Single fluid temperature regulation. Where is single fluid thermoregulation applied? It is a type of temperature regulation that is used in the pharmaceutical or chemical field for the temperature control of production machines, such as reactors, filters, mixers, blenders, where we need to maintain temperature control with ramp up and ramp down cycles, therefore with a processing range of the product that goes from a low temperature to a high temperature and vice versa, where there is a need to cool or heat the product. What occurs in practice? Let's analyze the typical scenario. Reactor in pharma process produces active ingredient. It must be heated from room temperature. Once heated, it must be kept. Once kept at temperature, cooled to a certain level, then maybe heated again, and so on. Typically, reactors are utilized with half-tube jackets or with an exchange jacket. In practice, in this shirt, a hot or cold fluid is circulated depending on the temperature level that we need to achieve with the product inside the reactor. In the past, and often still today, depending on the desired thermal cycle, either steam or hot fruit or diathermic oil is passed through this jacket, this half-tube, when we need to heat it. When cooling is required, steam is fully discharged, chilled water or water mixed with antifreeze is circulated internally to achieve extremely low temperatures. Clearly, all this involves times related to emptying and filling the jackets with the fluid. So if I have steam inside, I have to empty the condensate, drain everything, and load with chilled water, especially if I can't use chilled water with the diathermic oil. But I will have to create separate circuits, in essence, a series of implications that determine slowdowns in productivity. In addition to the fact that we have a relatively valid, relatively accurate temperature control, over the years, this single fluid technology has developed. What is it? In practice, the same utility fluids are used, such as steam, thermal oil, hot water, chilled water, and water with antifreeze, but they are made to work on a battery of heat exchangers, in which a fluid circulates that can withstand this temperature range, so it can work with a very high temperature range and is circulated inside the reactor jacket. The advantages are evident. I no longer have the dead times of unloading the shirt, reloading. Above all, I do not have the risk of mixing due to incorrect maneuvers for which glycolated water ends up in the boiler, or condensation ends up in the refrigeration unit, diluting our glycol, our antifreeze, with the risk of freezing. Well, let's say it offers a range of advantages. There are also disadvantages. We lose a bit in terms of heat exchange because we need utilities that are necessarily higher or lower in temperature than what flows inside the jacket. But I guarantee you that from an operational point of view, it is absolutely a solution now. Accepted, that is increasingly adopted at the expense of previous solutions. This is because the risks of fluid contamination are high. Having glycol ending up inside a boiler or vice versa, condensation ending up inside a chiller that needs to operate with glycol are very risky elements from the point of view of temperature control. There is no comparison. We can act with modulating valves or with a system of bypass valves and regulation that allows us to have an extremely fine and refined level of temperature control with very high temperature change speeds. This is a solution now fully embraced. If you have doubts, reach out. Greetings to all and thanks for your attention.